Hey guys.
I have a quick question before class
Yep.
starts.
Mhm.
Let me just pull out my.
Okay, let me finish writing this down. I'll come over.
So, it's the problem with Florida. And basically, I'm in a situation with one equation and two unknowns.
Okay.
So I don't know if I'm missing stuff. I don't know how to solve this, but this is the problem right here, right? So
Okay.
the rod.
Yep.
Fixed on this end.
Yep.
Body force.
Yep.
10 kips, length 20 inches, right?
Okay.
So this is the strong form solution.
Okay.
You don't have to look over this now. Maybe at the end of class, you can just let me know.
Sure.
Filled it all in correctly.
Yeah.
But then now, so that then they want the weak form, right?
Yep.
And
Assuming linear
we're
function.
assuming linear.
Yep.
Okay. So we have our fixed condition, right? And that's at 0. So
Okay.
they're both equal to 0, right? On the other end, like
Yep.
this is both equal to 0.
Yep.
So then we end up in this situation. And then we have this.
Yep.
And we do have the Neumann at the end, right? 10 kips.
Yep.
So it's W20.
Mhm.
And then this is just 10 kips over 1 inch squared. So it turns into 10
Sure.
kips.
Mhm.
Times 1, that's the area right there. So I have this.
Mhm.
And I have this. So that's just B1,
Mhm.
A1.
EA is
EA is
2000.
20,000.
Okay.
Then I've got W of X, so it's B1X
Mhm.
times the body force, which is this.
Mhm.
And then do it all out. I end up with this situation where we have one equation and two unknowns.
Remember, we're not really solving for the B's, and so we actually don't really care what this is. And actually, if you look at this, the B1's gonna cancel out
Yeah.
this B1.
Oh, I thought we cared about the B ones.
No, we don't care about that.
Oh, I thought that was the one that we cared about.
No, the A's are the ones we really
Okay,
care about.
the eight, so yeah,
Yeah.
we just divide this over and that will give us the value. of A1.
Exactly. Yeah.
Okay, I was really confused because I was like, okay, if we divide over B1, we'll get A1, but then comma was like, well, we only have one equation, we can't plug it back in. Okay, so it doesn't matter, A is what we want.
Exactly. Yeah. So remember, W is just the weighting function. So
Okay.
it's the main purpose of the weighting function is just so that we can get this basically.
Mhm.
So we get two first order derivatives.
Okay,
Besides that, we don't really care what the weighting function is. And most and if you do everything right, all the B should cancel out.
okay, all right, perfect. Thanks, Dr. Shan.
Yep. All right, it's 7 o'clock, so let's go and get started. All right, good evening, everyone. How's everyone doing today?
Great.
Good, good. Yeah, so the class before our midterm exam, and so that's always fun. It's always like a kind of like a half week for me, I guess. I did worked really hard last week to write the exam, and today and this week I only have to lecture once, and so it's kind of the nice thing about it, about the exam. Although you guys probably feel the opposite about the exam. Okay, so today we're going to continue our set of lecture notes on isoparametric elements. Right? I think kind of like what I've talked about last time. I think this is probably the most important lecture notes for this entire class. I mean, first of all, it leads directly into the project, and hopefully we get to the algorithm today, because that algorithm is basically what you're going to use for parts 1 and 2 of your project. And so if you can kind of get the isoparametric algorithm down, that's already 2 parts of the project, and like almost like 80% of the points I think kind of knocked down. Okay. And so I think that's about it. I know homework is due tonight, and so I plan on posting the solutions for the homework pretty much right after the homework is due, and so you can expect that to have that available to study to help you out with the Gauss quadrature. All right, and so are there any questions I can answer before we get started?
We can talk about what's going to be on the term at the end.
Sure. Yeah, we can talk about that, or we can talk about it now, I guess. Or did you have specific questions of what's going to be on the midterm? Or?
Yeah, so is it going to be like 1 strong form, 1 weak form, 1 finite element, like, and some conceptual questions, or how's that going to look?
Yeah, so the format's going to be the same as the first exam. So you'll have 4 conceptual questions that you have to answer, and then 3 problem-solving questions. And then, and so I won't tell you what the problem-solving questions consist of, or the exact topics, but you should be prepared for everything that you mentioned. So like strong forms, weak forms, finite element forms, and Gauss quadrature as well. So.
And no 2D finite element.
No 2D finite element. So that's just that's just busy work. That's not testing for anything significant. Yeah.
Are we gonna have something similar to like the current homework, the last problem 3?
No. So the last problem 3 on the homework, that's the 2D finite elements. So
Okay.
yeah, so that's just I have no doubt that you guys can do it, but whether you can do it in 75 minutes with all the other problems, I think it's an exercise in how quickly you can write, which is not which is not what I always want to do, but then apparently my last exam was kind of like that. But for your guys' exam, we're not going to do that. Okay. All right. Any other questions before we get started? Okay. All right. So let's go ahead and keep going. Okay. And so what we're continuing our lecture notes on the isoparametric method. How many questions? So there'll be 4 conceptual questions and 3 problem-solving questions. Yeah, no problem. Okay, And so just to recap, the isoparametric method is basically I would say what a lot of modern finite element codes are built on, right? And so, just like we motivated before, right? When you have a generic CAD model, a generic CAD file, and you load that into like ANSYS, we've seen before that a big step of that is producing a mesh on that element, on that structure, right? Okay. And so when you produce this mesh on an arbitrary CAD model, you end up with a lot of elements that are arbitrarily orientated. Okay. Right. And so all of the elements might have the same shape in terms of the number of edges, the number of points, but they're all going to be different orientations of that shape, just to make sure that those elements can fit within the CAD model, right? So to make sure that you have an accurate representation of your geometry. Okay. And so, for example, the one that we've been working on is a quadrilateral element, right? And so, if you have like a four-sided element, a four-pointed element, there's lots of different combinations of ways that you can arrange it, right? So you might have one that looks like this, okay, more like a trapezoid. You might have one that looks like a something like a rhombus. I think that's what it's called, right? Maybe I'm wrong. Forgot my shapes. Okay. And so you're going to end up, the point is you're going to end up with elements of lots of different orientations. Okay. And eventually, what you need to do in order to solve the finite element problem is you need to compute your element stiffness matrices and your element forcing vectors on these elements. Okay. Okay. And as we've been saying for the last few weeks, that in order to compute element stiffness matrices and element forcing vectors on this general finite element method, that involves performing integrals, right? So integrals across the element. But the problem is that when you have elements that are arbitrarily orientated like this, it becomes really difficult to evaluate these integrals. And so what we want to do instead is that instead of performing the integrals on these ones, we want to perform the integrals on a parent, what we call a parent domain. Okay? Okay. And so for a four-node quad, we have the parent domain that looks something like this. Okay. And so we have a square domain with all right angles. Okay. The origin of the is placed at the center of the square. Okay. We call the x-axis epsilon. We call the y-axis eta. Okay. And the vertices of this square are given by different multiples of 1 or -1. Okay. And so this top left one is 1, 1. Bottom right one is 1, -1. Bottom left is -1, -1. Okay. And the top left here is -1, 1. Right. So those are the points of all the vertices. Right. And the node numbering is we start with 1 in the bottom left, and then we go counterclockwise around from there. So we go 1, 2, 3, and we end up with 4 in the top left. Okay. Right. And so, for performing integrals, we like this domain in particular because when we're performing integrals for like the element stiffness matrix, right, we're basically be integrating across this entire domain, right? And so to perform that integral, we would have a double integral, okay, where the x bounds here, the x bounds goes from -1 to 1, and the y bounds also go from -1 to 1, okay? Or I guess, you know, it's f of epsilon and eta, or and d epsilon d eta, but you know, you get the idea. Right? And this is great for us because, you know, whenever we have integration bounds that go from -1 to 1, we know that we can use our Gauss quadrature to evaluate these integrals. Okay. Okay. And so we were kind of right in the middle of doing that. Okay. And so before we move forward, let me go ahead and write out the shape functions, our 4 shape functions, as well as their derivatives, because we're going to use them later on. Okay. Remember, when we're using Gauss quadrature for finite elements, we rely on the shape functions to perform a lot of our actions. Okay. And so since we have 4 nodes in this element, we're going to have 4 shape functions. Okay. And so we have n1 of epsilon and eta is equal to 1 over 4, 1 over 4, 1 minus epsilon, 1 minus eta. Okay. N2 of epsilon and eta is equal to 1 over 4, 1 plus epsilon, 1 minus eta. Okay. And 3 epsilon eta is 1 over 4, and we have a plus on both terms. Okay, so 1 plus epsilon, 1 plus eta. Okay. And finally, n4 is 1 over 4th, 1 minus epsilon, 1 plus eta. Okay. So these are the 4 shape functions that correspond to our isoparametric element that we had above. Okay. And because we'll need them later, you know, let me go ahead and evaluate all of the shape function derivatives, all 8 of them. And so it's going to be a lot. Okay. Right. And so because we have 4 shape functions here and we have 2 spatial variables, when we compute the derivatives, we have to compute the derivatives of all 4 of them with each spatial variable. Okay. So I'm going to do all the derivatives with respect to epsilon first. Okay, so we have partial n1 partial epsilon is equal to minus 1 over 4, 1 minus eta. Okay. We have partial n2. Okay. I'm writing this down because I don't think we got to it last time, and so I want to make sure you guys have it in your notes. Okay. I know it's a lot to write down though. So we're getting it out of the way first, and then we can focus more on the theory later on. I'll zoom back out. Again, let me just write this first. Right, so those are all the derivatives with respect to epsilon. And so now I'm going to write the derivatives with respect to eta. Okay. All right, so those are our 8 shape function derivatives, you know, for isoparametric rectangle. Okay. All right, so we'll get all the heavy writing out of the way, and then we can talk about how we actually use these to evaluate our integrals. Okay. All right, and so that's just kind of a recap. And so that's kind of the general idea about the isoparametric approach. And here are kind of all the formulas that we're going to need kind of along the way. Okay, and so what we're going to do next is we're going to work on how to evaluate each of the integrals in our weak form using this isoparametric approach. Okay. All right, any questions on this so far? Okay. All right, so let's take this kind of one integral at a time. And so, we'll start with the element stiffness matrix, and then we'll work on the element forcing vector after that. Okay, so we have in total three integrals that we need to evaluate. Okay. And they kind of go down in difficulty. And so I would say the element stiffness matrix is the most difficult, and then from there it gets a little bit easier. Okay. Excuse me. Excuse me. I never noticed this about myself, but my roommate in college told me one day, he said, I never sneezed just once. I always sneezed at least twice in a row. And ever since he said that, I've been keeping track of it in my life. And he's right, I never sneezed just once. Okay, element stiffness matrix. And so element stiffness matrix is a double integral of the gradient of W times K times the gradient of T dA. Okay. And so this is just the general from our weak form. Okay, so this is applied in the physical space, and so that means this integral is being applied to our arbitrary element. Okay. Okay. And so in order to evaluate this, we could try to integrate this in a physical space. I'm not saying that's impossible. It's just, really inconvenient at times. And so the way this is typically done is, just like we always do with our integrals, is that we perform a change of coordinates into our parent coordinates. Okay. Okay. And so we'll kind of do that step by step. Okay. This one's a little bit more difficult than our usual Gauss quadrature, because we have derivatives here. Okay. And so I think we kind of started talking about this at the end of lecture on Wednesday. And so not only do we have to change the integration bounds, not only do we have to perform a change of coordinates there, but we also have to change the coordinates of the derivatives themselves. Okay. Okay. And so what I mean by that is that not only do we have to get this, okay, okay, not only do we have to get that, which is the change of coordinates on the integration bounds, but we also have to get, we also have to perform this transformation as well. Okay, so when we have, you know, and we know this from 1D that, you know, when we take the gradients, right, we have derivatives like this, right? So we have partial n, partial x, and partial n, partial y, right? And so I'm just using n1 as an example, but, you know, of course we would have, you know, the shape function derivatives in all the directions, okay? And so we also have to transform this into okay. Right? And so not only do our integration bounds have to change, but the variables that we take the derivatives of also have to perform that same change of coordinates. Okay. Okay. And so there's kind of two levels here. Okay. And so let's start with the first one. Okay. Because the first one we've kind of done this already. It's just we haven't really fully done it in 2D. Okay. And so to perform this step, you know, we not only just change the bounds, but we have to make our substitutions as well. Okay. Right, and so the first step for that is that we change the bounds. Okay, we change it to -1 and 1. Okay. Next, we have to make a substitution for our integration variables. And so whenever we see x, whenever we see y in the integrals, here it's not going to matter too much because most of the time we have linear functions. But you know, this step is still used for the source function later, which we'll see. Okay. And so if you recall, you know, one step that we did before when we first formed our shape functions was that we formed our physical coordinate function as well. And so that's x of epsilon and eta, and then y of epsilon and eta. And so we have to plug those in. Okay. And the last thing that we did was we multiplied by our scaling factor. Okay. Okay. So remember, our scaling factor is given by our Jacobian, right? So our Jacobian kind of represents the transformation between those two, and our scaling factor is given by the determinant of that Jacobian matrix. Okay. Okay. Where the Jacobian, remember, it's a matrix in 2D, is equal to partial x, partial epsilon, partial y, partial epsilon, partial x, partial eta, partial y, partial eta. Okay. And so we have the 2x2 matrix, which represents kind of the scaling factor, how much we have to scale in between x and epsilon and eta. Okay. And the determinant of that kind of represents that change in area. Okay. Okay. And so I'm not going to go too much into that step, you know, just because we've kind of seen that in 1D, and we'll see this step again once we do the thermal generation integral. But I want to focus most of my attention on step 2, which is the transformation of the derivatives themselves. Okay. All right, so let's kind of focus on that. All right. And so just to remind you, you know, let me go ahead and write out the functional form or the vector form for gradient of w and gradient of t. Okay. And so gradient of w looks something like this. And so if we put it in matrix form, we have this matrix with all of the shape function derivatives with respect to the physical coordinates. Okay, so we have partial n1 partial x, partial n2 partial x, partial n3, and partial n4 as well. Okay, then our second column here is all the same shape functions, but taken with respect to the y. Okay. and then gradient of t is given by same thing, but just kind of but transposed. Okay? Okay, so that's the matrix form of the gradient of t. Right? Okay. Where again, remember T1, T2, T3, and T4. Those are the values of the nodal solutions at each node of our element. Okay? Right, so that's fine, right? And so this is a fine expression. And so remember when we did this with the 2D triangle, in physical coordinates, we had basically formulas that we plugged in for each of these cases. So they involve the area of the triangle and the different coordinates of that triangle. Okay. The problem now is that because we're working with an arbitrary element, okay, an arbitrary rectangular element, our n1, n2, n3, and 4, our shape functions, are not given with respect to x and y, right? So they're given with respect to epsilon and eta, right? So that's kind of what we had up here. Okay. And so we can't actually evaluate these, but what we can do is we can use the information from the Jacobian to transform those derivatives into epsilon and eta derivatives, okay? Okay. Right? Because if you look, right, if you look at our Jacobian here, right, so this is Jacobian as we defined it. If we take the inverse of this matrix, and that's something you can do, right? You can take inverses of matrices. You end up with quantities that have epsilon and x, the parent and the physical coordinates kind of inverted. Okay, and so if we look at Jacobian inverse, okay, what we get is partial epsilon, partial x, partial eta, partial x, partial epsilon, partial y, partial eta, partial y. Okay. Okay. And so this right here is a 2x2 matrix, right? And so what if we take this 2x2 matrix and then we, and then we combine it together with the shape function matrix, that's taken with respect to the parent coordinates. Okay. Okay. And so let me just do it for gradient of t, but you can imagine kind of the same thing taking place for the gradient of w as well. Okay. And so let me just write the same gradient matrix, but let me take all the derivatives with respect to epsilon and eta instead. Okay. And so what if we had, so partial n1, partial epsilon, partial n2, partial epsilon, okay. All right, so that's the same shape function derivatives matrix, except now, I took it with respect to epsilon and eta, okay? And the good thing is that everything in this matrix we can actually evaluate because N1, all of our shape functions are given with respect to those variables. Right? And so that's a great thing for us. And so whenever you can evaluate stuff, that's a good thing, right? Being able to evaluate something's better than not being able to evaluate anything. Okay? And so that's great, you know, but that's not what we want, right? What we want is up here. So what we want is the shape functions, their derivatives with respect to physical coordinates. Okay. Well, let me do this. And so, you know, together with this matrix down here that we can evaluate, let me combine it together with the Jacobian inverse. Okay, so let me go ahead and plop this right here. Okay. And I'm going to pre-multiply this by our Jacobian inverse. And so we're going to have partial epsilon, partial x, partial eta, partial x, partial epsilon, partial y, partial eta, partial y. Okay. Okay. And the nice thing about this too is that just like its partner on the right, you know, because we can evaluate the Jacobian, we can evaluate its inverse as well, right? Because any 2x2 matrix, it's a very simple function to do in MATLAB just to take its inverse. Okay. And so we can evaluate both expressions here. Okay. And so what we have here is a matrix multiplication, of course. And so, you know, again, this is something that you normally would not do by hand, although we will do one by hand at the end of these lecture notes, just you know, just to kind of show you in action. But let's see what the size of the matrix that results. And so we have here a 2x2 matrix. Okay, right, a simple square matrix. The matrix that's multiplying by has 2 rows and 4 columns. And so this is going to be a 2x4 matrix. Okay. And so since we have a 2x2, we multiply by 2x4. We look at the inner indices here. Okay. We see that these two are the same. And so since those two inner indices are the same, that means this evaluation is compatible. And so we can actually perform this with this multiplication. And what we end up with is another 2x4 matrix. Okay. Okay. And so that's what the results as a result of this operation. Okay. Okay. And so I'm not going to evaluate every single expression in that 2x4 because that's madness. But I will show you a couple of those. Okay. And so let's do this row multiplied by this column right here. Okay. And so I'm just going to do the first entry of the matrix multiplication. Okay. And so if we multiply those two, we take their dot products, we get partial epsilon, partial x. Okay. Multiplied by partial n1, partial n1, partial epsilon, plus partial eta, partial x, partial n1, partial eta. Okay. And so what does this give us? Well, you know, it's kind of hard to evaluate what each of these give, but what you can kind of see is that we have these terms kind of cancel out. Okay? They don't actually cancel out because that's not how calculus works, and so calculus is not like algebra. But what this is right here is this is the result of a chain rule differentiation. Okay. Okay. And so what is a chain rule of? It's a chain rule of this. Okay. Okay. And so if you kind of recall how the chain rule works, and so you know, if your function n is a function of you know 1 or 2 variables, but then you take the derivative of it with respect to a different variable, then this is kind of how you evaluate the chain. the chain rule. And so first you take the derivative of the function with respect to the variable that it is a function of, okay, which is epsilon and eta, and then you take the derivative of that variable with respect to, you know, the one that you're taking the derivative. Okay, so that's like a seashell kind of by the seashore kind of thing, but you know, I think everyone's kind of seen chain rule in this class at some point or not. Okay, basically is, you know, when we want to take the derivative with respect to x, we have to take the derivatives of all the inner terms as well, which is epsilon and eta. Okay. And let's do one more just to kind of prove to you that it works. And so let's do this row right here, and let's do this column. Okay. And so if we evaluate that, we have partial epsilon, partial y, partial n3, partial epsilon, plus partial eta, partial y, partial n3, partial eta. Okay. And so just like the pink, its pink brother above, you know, this is the result of chain rule as well. At the chain rule of partial n3, partial y. Okay. And so what we can say is that this multiplication of these two quantities, the Jacobian inverse and the shape function derivatives in the parent coordinates, actually gives us exactly what we want, right? Because what we wanted, you know, where we started was up here, right? And so we wanted a matrix, in this case, a 2x4 matrix, which was the shape function derivatives in the physical coordinates, okay? And so what we can say is that we can achieve that same thing by multiplying these two matrices, okay? And the good thing about evaluating these two matrices is that we know how to evaluate these because, you know, just because of how we structured the shape functions, okay? And so this is kind of the, you know, the manifestation of that, the kid saying, I want this, right? And the mom saying, we have this at home, and this is what we have at home because, you know, we have all everything in terms of the parent coordinates, okay? All right, so that was kind of a really long explanation of that, but I kind of wanted you to see every single step of this and how we obtain that, because I think this is kind of a big step. Okay. Next, I'm gonna summarize this into you know, a single expression, and you'll see exactly how the element stiffness matrix is evaluated using this isoparametric concept. Okay. Okay, but are there any questions on kind of what we've done here so far? Okay, all right, so let's go ahead and put it together. Okay, and so using this idea, our element stiffness matrix is now okay. And so we're going to have a double derivative here, or double integral, excuse me. Okay. The first thing we have to evaluate is the gradient of W. And I know we have W1, W2, W3, W4, but, you know, because those belong to the weighting function, you know, we don't really care about them. And so we're just going to leave them out. And so what we have is the following. First, just going to color code this. Okay. And so first, what we're going to have is kind of the transverse expression of what we have above. And so we have partial n1, partial epsilon, partial n2, partial n3, partial n4, partial epsilon. Okay. And the same thing with etas. Okay. But remember, you know, we don't want the shape function derivatives in the parent coordinates. We want them in the physical coordinates. And so the way that we fix that is we multiply by the Jacobian inverse. Okay. But since this is transverse, I'm going to post multiply it, right? And so I'm going to multiply it on the back side. Okay. So I'm just going to do Jacobian inverse for that. Okay. And so both of these together, this is gradient of W. Okay, so that's kind of where we got this this term right here. Okay. The next thing we multiply is K, the thermal conductivity, and so good old K doesn't really change. He's just a constant. Okay. Next thing we have, of course, is the gradient of T, and so that's exactly what we expressed up here. Okay. And so the gradient of T here is going to be the Jacobian inverse. Okay. This time we're pre-multiplying it because of how we structured that. Okay. And then we have all the shape function derivatives with respect to the parent coordinates. Okay. So we have partial n1, partial epsilon, partial n2, partial epsilon, partial n3, partial epsilon, partial n4, partial epsilon. Okay. And all the same things with respect to eta. Okay. And so these two together in blue, this is gradient of T. Okay. Let me go ahead and zoom out just so you can see everything. Okay. Okay. Right. And so those are the transformations of our derivatives into the parent coordinates. Okay. Next, we have the transformation of the integral itself, right? So that was kind of the first thing we did. And so we're going to multiply here by the determinant of the Jacobian. Okay, can't forget that. Okay. And then we have our integration variables, which is epsilon and eta. Okay, so we have d epsilon d eta. Okay. And of course, our integration bounds, because we perform that change of variables, is -1 to 1 on both epsilon and eta. Okay. And so this entire thing right here, this is our element stiffness matrix in 2D using isoparametric elements. Okay. And specifically, this is for an isoparametric element, okay? Isoparametric rectangle. Yeah. Inside the determinant is Jacobian, so it's determinant of J. So J here, remember, J is our Jacobian. Yeah. All right. And so the one you're going to do for the project is, it's not as intimidating as this, but it's close. And so remember, your project is a triangle, and so it has 3 shape functions instead of 4. But the basic idea is the same. Right? And so after we're done kind of going over the theory, and so next we have the element forcing vector. I'll kind of sum the whole thing up for you in an algorithm that's kind of custom tailor made for MATLAB. Okay. And so that algorithm can be used for parts 1 and parts 2 of your project. Okay. But I wanted to go over the theory first to kind of explain, why we're doing each step. So kind of why we're changing the integration bounds, why our shape functions, our derivatives are now in the other coordinates, where all the Jacobians coming in. And so I want to make sure, we have all that covered, just so that when we go over the MATLAB algorithm, it all makes, a little bit more sense. Okay. And of course, it goes without saying that, this is just way too many calculations, not only the matrix multiplication, but also all the inverses, all the determinants, right? So this is not something that you would normally do by hand. And so this is meant to be a computer algorithm. Okay. Any questions on this? Okay. All right, and so that's the element stiffness matrix, and so that's you know the hardest part by far because we have the derivatives to handle. Now we have the element forcing vector, and so those get a little bit easier. So let me go ahead and zoom in a bit just so I can just so my pen is thick again. Okay. So element. So this is the element forcing vector using isoparametrics. Okay. So let me write out this general expression first in physical coordinates, and then we'll go through the same process of transforming that to the parent coordinates. Okay. And so our element forcing vector in physical coordinates, first we have the thermal generation term. So this is going to be a double integral across our element, okay, of n1, n2, n3, and 4, okay? And this is all a function of x and y. Okay. And we multiply this by s of x and y dA, okay? And then we have the Neumann boundary condition term. And so the Neumann condition is going to be a line integral. Okay, so I'll denote the line integral with the single integral with the circle through it. Okay. And we have n1, n2, n3, n4. Okay. x, y, x, y, x, y, x, y. Okay. Q bar ds. Okay. And so this, of course, right here is our thermal generation. Okay, and this is an integral over the area because we have the double integral there. Okay. And then this expression right here, this is our line integral across the Neumann boundary. Okay. Okay. And if you're curious about how this breaks down into your project, you know, this first integral here, this is part 2. Okay. And the Neumann boundary, this is part 3. Okay. And the element stiffness matrix, I didn't say up here, but this is part 1. Okay. Okay, so those are the 3 parts of your project. Okay, so part 1 is do element stiffness matrix, so that's the bare minimum you need to get a solution. Part 2 is to implement a forcing function. And part 3 is to implement a Neumann boundary condition. Okay. And so these are the integrals that we have to evaluate. And just like we saw for the element stiffness matrix, we need to transform these into the parent coordinates, of the isoparametric coordinates. Okay? So all this x and y, you know, we need to transform that into you know, into epsilon and eta. Okay. The good news is that, you know, for these integrals here, you know, we have a lot shorter or a lot simpler of a task, you know, because we don't have any derivatives. Okay. Okay. And so let's do part 2 first. So let's do the thermal generation integral. Okay. And so for this integral, we just have to perform, the change of coordinates on the integration bound. Okay? And so for this, we have to just change the bounds. Okay. Right. Next, we have to substitute in for x and y. Okay. So we're going to substitute for x of epsilon and eta and y of epsilon and eta. Okay. And so that's going to eliminate x and y from our, from our integral. And so now we're going to integrate over x and epsilon and eta. Okay. I have no idea why my iPad's doing this. Just trying to draw a straight line, iPad. Come on. Okay, close enough. Okay. Okay, so that's the second thing we have to do. And the third thing we have to do is we have to add in our scaling factor, which is our determinant of our Jacobian. Okay. Okay. And so no derivative nonsense, so no inverse Jacobian or anything like that. Okay. And so we can sum this up in just kind of one step. And so, the shape functions are nice because we already have the shape function in terms of epsilon and eta. And so when we perform this this change, we end up with the following. And so we have integral. Okay. Both these are going to go from -1 to 1. First, we substitute in for the shape functions, but the shape functions are already given in terms of epsilon and eta. Okay, and so we have n1, n2, n3, n4. Okay, and all these are already epsilon and eta, epsilon and eta, epsilon and eta, epsilon and eta. Okay, so those we already know. We just pop those in place. Okay. And the only other thing is that our thermal generation function here, which is a function of x and y, now will be a thermal generation function of x of epsilon and eta and y of epsilon and eta. Okay. Okay. And then we multiply by the determinant of the Jacobian. Okay. And then our integration variables are, of course, the epsilon, the eta. Okay. And so we kind of sum that up in just one step. Okay. All right. And so I think the key point here, which I think is the most difficult to do, is the substitution. Okay. And so this is probably where you're going to make the substitutions more so than the element stiffness matrix, because the element stiffness matrix usually doesn't have x and y. Okay. And so just to recall, the way we obtain x of epsilon and eta is that we use the shape functions, right? And so x of epsilon and eta is equal to x1 and 1 of epsilon and eta, okay, plus x2 and 2 of epsilon and eta, plus x3 and 3 . How the hell does that happen? Oh my God. Apple products are so shit sometimes. Right, and so the way we obtain this is we just use our shape functions and we use x1, x2, x3, x4. Well, remember x1 through x4, those are the physical x coordinates of our original element. Okay, and so remember our original element belonged in physical space, and so each of those nodes had their x coordinates. Okay, and same thing for y as well. Okay, so y of epsilon and eta is equal to y1 and 1 plus y2 and 2 plus y3 and 3 plus y4 and 4. Okay. Right, and so you actually get a fairly long function for this, especially in 2D, right? Because our shape functions are fairly large, you know, and we have four terms here. Okay, but remember, you know, we're not actually, you know, integrating over that entire function. We're only going to be evaluating these at the Gauss points. That's the point of Gauss quadrature. Okay, and so even though these are long functions, okay, we only need to evaluate them at the Gauss points. Okay, which when you're writing code is a lot simpler to do because they end up just being just a single line of code. Okay, and we'll go over that, you know, once we go over the algorithm as well. Okay, but that's the general idea with the with thermal generation function. And so it's only about half the work that you do for the element stiffness matrix, again, because there's no derivatives involved here. It's just a straight up change of variables for the integration paths. Okay, the only thing is that, you know, you might have to work a little bit harder for x and y as opposed to, you know, the element stiffness matrix. Okay, which traditionally usually does not have too much x and y to it, unless you have a spatially varying thermal conductivity. Okay, any questions on this? All right, and so let's go over the Neumann boundary condition integral. Okay, and so, you know, I make this part 3 of the problem of the project because you know, when we do it for a square, it's going to seem not that bad, but when you do it for a triangle, it's actually, you know, a lot more complicated. So, you know, I know some of you are kind of already looking at this right now, and so for a triangle, it actually becomes a bit more complicated. But for a square, it's actually not that hard to explain. Okay, and so for our Neumann condition, okay, and so our Neumann BC is a line integral. Okay. And so I know people freak out a little bit, you know, when you hear, you know, line integral, surface integral, but, you know, for our kind of practical purposes, a line integral is actually no different than just a simple 1D integral. Okay. Right, and so a line integral is nothing worse than just a 1D integral. Okay, and especially because we're going to be evaluating it with Gauss quadrature, you know, we don't have to do anything you know, special in terms of, you know, the curve functions or any of that. Okay. I don't even know how it does this. No, it's full. It's weird. No. Oh. It always kind of does this sometimes, but today it's been like especially active. Maybe it's because I gave two other midterms today. So this is the first time that I'm using it this week. Okay. And so, when we're using Gauss quadrature, and we're performing our change of coordinates anyway, then it doesn't really matter, what our line integral looks like. It's because typically, when you have a line integral, what that means is that, you might be integrating over a generic path in space. Okay. And so you might be integrating over, something like this. Okay. Okay. When you integrate from point A to point B. Okay. And so that's kind of what people think of when they think of a line integral, is that you have kind of an arbitrary curve in space, and what you have to do is you have to parameterize the curve. Okay. And then once you parameterize the curve, then you integrate over that parameterized variable. Okay. And so that might still be true in our 2D finite elements. And so, our path might be curved, it might be, take lots of twists and turns, depends on the shape of the element. Okay. But we're going to be evaluating this with Gauss quadrature anyway. And so, no matter what path that we take, it's still just going to end up being a line like this, right? So we have -1 to 1, right? And so it doesn't really matter, and so if you have a line integral, it just ends up being -1 to 1 anyway, okay? And so don't be intimidated by the term line integral, because I know it's not a concept that's covered, a lot in math classes, maybe more so than others, depending on the instructor. But for our purposes, it's just a 1D integral that we're going to do with Gauss quadrature. Okay. And so to that end, we're going to have our line integral look something like this. Okay. And so we have integral with the circle, okay, of n1, n2, n3, n4. Okay. N1, N2, N3, N4, and we have our Neumann value, which for our purposes, for this class, we'll assume it's constant. But it's possible to have spatially varying loads and things like that. And so this can very easily be like a function of x and y. Okay. Okay. And so if we transform this, we're going to transform this into a Gauss integral. Okay. Okay. And so our Gauss integral here is going to have all epsilons and etas. Okay. So we have n1, n2, n3, n4. Okay. Okay. All epsilons and etas. Okay. Then we have q bar. Right. Then we have our Jacobian. ds. Okay. But we can go ahead and plug in an expression for that Jacobian, right? And so remember in 1D, and you saw this with the homework as well, that when we have our 1D Gauss quadrature, right, this Jacobian just ended up being the length of our integration bounds divided by 2. Okay. Okay. Right. And so I think, in the in-class example, we had integral from 0 to 5, right, of some integral, right? So dx. And so when we transform this, we have integral from -1 to 1 of that integrand, but the Jacobian that we multiplied by was the length of this domain, which is 5 divided by 2, right? So that's kind of the factor that we have. Okay. And so when we're evaluating line integrals, we just kind of make that substitution already. So instead of making a generic dx, d epsilon, what we just say is that this is just going to be the length of the line divided by 2. Okay. Okay. And so particularly, since we're evaluating this integral across the Neumann boundary, that L right there is just going to be the length of that Neumann boundary. Okay. And so the length of the Neumann boundary, we divide it by 2. Okay. And so that's going to be our Jacobian. Okay. Okay. All right. So that's our line integral. Okay. But we have something that's a little bit of a discrepancy here, right? Because, we have just one integral here, right? But, we have 2 variables, right? And so we have both epsilon and eta. Okay. Okay. And so the question is, how can we integrate both variables with just one integral? Okay. Evaluate both variables just one integral. Okay. Right? Because when you integrate something, that only works on just one variable at a time. And so if we have 2 variables here, how are we going to do that? Okay. And so the answer for that is kind of just based on what our element looks like, right? And so let me go ahead and draw our element again. Okay. And so there's our element. Okay. Most of the time, and there are some exceptions, if this element was in a corner or something, right? Most of the time, only one edge on this element is going to be on the Neumann boundary. Okay. At most, it's going to be 2, but or 3. Okay. But for the vast majority of cases, I'd say 99% of cases, only one of these edges are going to be sitting on the Neumann boundary. Okay. Okay. Right, let me illustrate that for you, right? And so let's say that we have kind of an arbitrary, structure like this, okay? And let's say we have elements that kind of look like this, okay? And let's say that on this edge right here, okay? I think it helps if I keep my palm off it. So I'm trying really hard not to put my palm on my iPad, okay? On this edge right here, we're applying a heat flux Q, okay? So that's the Neumann boundary, is that heat flux, okay? And so if we look at an element that's sitting on this boundary, right? And so we look at this element here in blue, okay? And we kind of zoom that one out. Okay. If we consider, which of these edges are actually being heated by the heat flux, it's only going to be this right one, right? right? All the other edges do not have a Neumann boundary condition evaluated on it, okay? And so when we evaluate this integral here, that means we only have to apply the Neumann integral on that edge, okay? Okay. Right. And so let's see how that applies to our parent domain, right? And so let's say, that Neumann integral is being evaluated only on that right edge of the square, okay? Right. What do we know about the path of that line, right? And so for this entire line, epsilon is a fixed value, right? And so when you go from the bottom of the line, and so let's say that we integrate this way, right? So we integrate from bottom to top. Okay. And so for this entire line, epsilon is going to equal to 1, right? Because it's a vertical line. So vertical lines have a fixed value of epsilon, or we traditionally say a fixed value of x, but in this case we have epsilon and eta, and so we have just a fixed value epsilon. Okay. Meanwhile, eta is the one varying from -1 to 1. Okay. And so when we go to evaluate this integral up here, okay, we're not actually integrating over 2 variables. We're only integrating on 1. Okay. And so the other variable that we're not integrating over, we're going to hold fixed. Okay. Okay. And so for this particular line right here, okay, so I'm still using this one as an example, but we can apply the same idea to all the other edges. Okay. And so for this particular line, if we want to perform the Neumann integral, right, we'd integrate from -1 to 1, right? We have all our integrands, which involve the shape functions and the Neumann value, which I'm not going to repeat here, okay? But we're going to integrate this over eta, okay? So we're going to have one integration bound, which is eta, okay? For all of this stuff, okay, which includes the shape functions, we're just going to set epsilon equal to 1. Okay. All right, and so I'll give you kind of one final mathematical expression for it, and then we'll wrap it up for today. Okay. Okay. And so to wrap this up into kind of like one nice expression, and so we have integral from -1 to 1 of n1, n2, n3, n4. Okay. First, let's do a case where we're integrating over the horizontal lines. Okay. Okay. And so on the horizontal edges, right? And so we're talking about the top edge and the bottom edge. Those have fixed values of eta, right? And so eta is going to either going to equal to +1 or -1. Okay. And so this is going to be we're going to integrate over epsilon for all of these, and so we're going to leave epsilon as kind of a free variable. Okay. But our eta is going to equal to either plus or -1. Okay. And we're just going to set that in right away. Then we have our Neumann flux. We have the length of the edge divided by 2. And we're evaluating over epsilon. Okay. And then if you're going to integrate over a vertical edge, we have kind of the opposite. Okay. Okay, so for vertical edge, we have integral from -1 to 1, and 1, and 2, and 3, and 4. Okay. And so for our vertical edge, our epsilon values are fixed, and so we have epsilon is equal to plus or minus 1. Okay, depending on which edge that you're on. So it's either going to be the left edge or the right edge. And we're integrating over eta. Okay, then we have q bar, L divided by 2. Okay. And we're integrating over eta, just like that. Okay. And so that's how we evaluate those integrals. Okay? So we're only evaluating just on one edge at a time. And we take advantage of the fact that our element is actually a square. Okay? And so when we evaluate on one edge, we're just going in either the vertical direction or the horizontal direction. Okay? And so that makes it a bit easier to evaluate our integrals. Okay. All right, any final questions on this before we wrap it up for today? Okay, so on Wednesday, we'll take our exam, and then Monday, we'll kind of put this all together into an algorithm, and then we'll apply that in writing once, so you can see that happening, just so that, to prepare you for the project, okay? All right, so I'll see everyone in class on Wednesday for the midterm. Remember, it's in person, okay? So remember to bring yourself, bring your writing utensil, bring your calculator, bring your cheat sheet, okay? And if you have any other questions on leading up to the exam, just let me know. I have office hours tomorrow, but if you can't make it, just send me an email, and I'll be happy to talk to you there. Okay, so have a great evening, everyone, and I'll see everyone on Wednesday. All right, question. So do you need two integrals when the Neumann boundary condition lies on the hypotenuse? That's a great question. And so you do not actually. And so you still just need one integral. It's just you have to set it up in a little bit of a different way. And so we'll go over that next week. Yeah. So after we go through the algorithm and after we go through that stuff. Yeah. Yeah. That's the part that I think trips most people up with the project. Yep. Yep.
Rest in terms, so I'm just gonna try to put it on my note here. Private element non-reference problem, can we expect to have more elements than this? Would you want us to discretize it over 2 elements? Like in the book, it's 4 elements, I think.
The most I'll ask you is 3.
Okay.
3. But you could take some shortcuts here. And so, use the fact that I'm going to ask you with linear shape functions. I'm not going to ask you quadratic. And so when you take the derivatives here, you end up with like 1 over the length, minus 1 over the length, 1 over the length. And so this just kind of all ends up out here because it's a constant.
Yeah.
And so you kind of take advantage of the fact to kind of speed up your calculation.
Okay. And we can expect to have all the stiffness matrices for each element and then build a global from there and apply boundary conditions.
Yep.
Okay. And we're not going to be expected to solve for
No.
it? Okay.
No, because you need a calculator.
Okay. Just wondering if I have any other questions. That I can just squeeze out of here. Okay, I think, yeah, I'm just concentrating mostly on doing the strong form, a weak form, one of these in Gauss quadrature.
Yeah, if you can do that stuff, then I took the exam today. It's shorter than
the exam. Did you ace it?
Of course, I wrote the questions. I know the answer because I wrote the questions.
Yeah.
But I just do it just to gauge how long it takes. So this one's definitely shorter than the first exam.
Okay.
Definitely a lot shorter.
Yeah, I remember in my 411 controls class, I think it was. She had us write our own like quiz, getting tough. This is the whole class, and then solve it ourselves. And it was like, it had to be like original, like it couldn't be something in the book or whatever. So That was kind of like putting yourself in a professor's mindset, which is,
Yeah.
which is weird.
It's hard coming up with questions sometimes.
Yeah, like original ones, definitely.
Yeah.
All right, thank you.
Yeah. Question. Yeah. Mhm.
So for
Yeah.
Yes. He said it should have gone to.
Yep.
Yeah, so for working instead of teamwork.
Exactly. Yep. Yep. So it's exactly the same. So heat conduction and elasticity, they're the same equation. You just substitute.
Okay. So they definitely do this here.
Yeah.
You put
It should be white. But this is not on the, this takes way too long. It's a 2D, it's all just 2D calculations. So,
No, that's what I was looking at. I couldn't get it.
yeah, it should be white. That must have.
I guess the one from the start.
Sure. Yeah, so strong form, weak form, they're the same problem. So they're just, you can think of it as different descriptions of the same boundary value problem. So boundary value problem is just a name for like a physical system that you want to analyze. And so strong form is kind of one way to describe it. Strong form is a differential equation. Weak form is just a different. So they're the exact same problem. Expressed. Yeah. So what would be incorrect to say like, oh, weak form is a different problem than strong form, which would people write because they look so different. Because one has no integrals, the other one does. But they're the same problem. And if you solve them exactly, which is the key is to solve them exactly, you end up with the same answer. And so the way we do it in class, we end up with different answers sometimes because we don't solve them exactly. So the strong form we solve exactly, but the weak form we solve approximately. And so that's the difference. But they express the exact same problem. And so if you find an approximate solution to the strong form, you're gonna get the same function. I present the strong form just because I think that's traditionally how people learn how to solve the math class. The weak form is something that's new. And that's the thing that leads into our finite element. So that's why I present the approximate solution. If we did kind of everything for everything, then we just won't have to come through. So that's why I end up focusing on those. But essentially, they are the same. Yeah. So the shape function is used to basically to interpret, right? Because essentially, if you think back to our direct stiffness method, when we solve for our solutions, we solve for the solution that we know. We solve for the displacement. So for general finite elements, you're doing the same thing. So you're solving essentially for the local solutions, but to form things like the element stiffness matrix and the element forcing vectors, you need to know how the solution varies within. As you go from node to node, how does the solution vary? And so that's what the shape function is used. The shape function is used to basically model how the solution varies between nodes. And that's needed mathematically for element stiffness. Boundary in multiple dimensions. And so in 1D, our boundaries are just the left and right. And so as you go up in complexity, like a 2D domain is like a surface, right? So the 2D, a blob or a square, whatever. The boundary around a 2D surface is kind of like what we talked about. For a 3D body, like you have a volume, then the boundary for that 3D surface, exactly.
So for the 1D, it's just the point.
It's just points.
Okay.
Yeah. Okay.
Oh, what do you mean by this?
Oh, that's like the Green's theorem, that stuff we did, when we did an introduction to 2D finite elements. And so that was kind of the whole Green's theorem, Green's formula. And so it's just basically applying integration rules to do that integration. And so integration by parts, the motivation for finite elements is a bit different.
the goal with integration by parts is to take that initial integral and split it up into a few different parts. So we have one part that has all those elements. And so that's our term of 2D issues, right? So instead of having one secondary derivative, we have two first order derivatives. So that's one goal. The other goal is to get something like that, which is a term that the value of all the values. And so that's kind of our two problems of integration. And so in 1D, we just use traditional integration by parts, just because most people learned it before. But in 2D, I think most people haven't learned it, so that's why we use green steel.
And then for this one, that has to disappear the duration.
Exactly.
That's the only one.
That's that, and it has to have the same functional form as our solution. So whatever function, whatever form we assume for the solution, the weighting function has to take the same. And so it's either linear, quadratic, or so it can't.
Okay.
Yep.
Alright, thanks.
Yep.
Can I ask you one more question?
Sure.
For the weak form, like it's a weak form, straight on that, this is always.
Not necessarily. So it could be on the right side. It could be but this is the case. I think we did this for specific.
Yeah, let me rephrase that. I'm not saying it's gonna always be at the, whatever that's. Yeah, but this is like wherever it's saying that it's.
Yes.
Right, right, so I think in this, I think in this case, I'm actually this one that.
Oh, yeah.
Okay, so that's always this is gonna be.
Yes.
Right, okay. Also for the Gauss quadrature, can we expect more?
We expect it.
That's great.
But not all of them are happening. Some will just be straight up integration balance, and then one or two.
Okay, fair enough. And earlier you were saying the shape functions are going to be.
Yeah.
In what case did we do shape functions out of line?
We never did any calculation, but we just kind of talked about what it kind of would be.
Okay, because I'm like, pretty much going straight into this.
Yeah. You should do it.
I'm not sitting there and actually refreshing.
No.
Okay, just making sure that I'm like, yeah.
Right. We talked about it for 1D, and even for 1D, we said this is a mess to do. And so once you get 2D quadratic stuff, it's huge. That you practically never do. But I know there's a lot of you coming from 540, so we talk about quadratic. Right. So I wanted to show you what that actually. Oh. But we never actually did.
Okay, I think you should be good.
Okay.
Thank you. Got anything?
I need to go call my grandma real quick.
Okay.
Let me just look at. So this is the problem. They want you to derive their own strong form. I said, okay. So I did part B and then part C, and then so this is the strong form, and this is the weak form.
Okay.
Can you just
Yeah.
all over?
Yeah.
Remember.
Sure. We have 0. You're showing me.
Yeah,
So actually,
it says 0, there's like that.
Yeah. Right. You're showing this. Finite element, surprisingly, it's very niche in terms of the classrooms. So there's not really that much out there. People mostly learn finite element stuff using professional. Answers will come to a lot of companies. I know they do a lot of training. People learn it that in terms of the fundamentals of theory, there's not that much. Even textbooks are difficult.
I mean, it's in the undergrad mechanical engineering. I didn't learn that.
Not here. It's in a like. So
Is it?
yeah, most places. The only one I think has it required, because I have a college. Kansas actually has a partnership with people that actually teach that class. And so if they're like, as payment for us using licenses for free, then you have to teach.
Yeah.
It's-
Yeah, I couldn't find stronger. This is probably some of the other programs. It's fine. I think it's
Yeah.
all something else.
A lot of the textbooks you'll see will have the direct stiffness method, which is what we did for the first time.
Yeah.
The strong and weak forms, these are kind of, a little bit more of a modern technique, I would say, developed really mostly in the 90s. So there's not that many textbooks. Actually, a lot of people use the same textbook that was actually written in like an ADD or something like that. It's written by someone from Tom Hughes. He's still alive, so that kind of tells you about modern. And then it is he knows his fine wine. Yeah, I think this was good too.
Okay.
Yeah, I mean, the arithmetic I didn't check, but the method looks good.
Okay.